Somewhere beneath the dry basins of Wyoming is the remains of a world that should not feel American at all. 50 million years ago, there was no sagebrush here, no cold winters, no open high desert. Wyoming was covered in dense, humid, subtropical forest. Palms and figs grew beneath towering trees, and the canopy was thick enough that sunlight reached the ground only in patches. There was no permanent ice anywhere on Earth. Palm pollen preserved in the rocks of Wyoming's Bighorn Basin confirms vegetation growing hundreds of miles north of where we would expect it today. Fossil crocodiles found in the Green River Formation tell the same story. This was a warm, stable world, closer in climate to modern Florida than modern Wyoming, and moving through those trees were primates. Not one unusual species clinging to the edge of its range. Dozens of them, animals with grasping hands, forward facing eyes, and bodies adapted to a life among branches. The Bridger Basin alone has produced skulls, teeth, and skeletons from one of the richest concentrations of early primate fossils ever discovered. North America had primates for more than 20 million years. They diversified here. They occupied different ecological roles. Generation after generation lived beneath American forests for a span of time far longer than humans have existed. Then they disappeared completely. The forests changed, the planet cooled, and eventually not a single native primate remained anywhere on the continent. But millions of years later, something appeared in Nebraska that should not have been there, a primate, alone in the fossil record, separated from the great American primate dynasties by millions of years, appearing on a continent that had seemingly already lost them all. For 60 years, scientists could not explain where it came from. Its existence would eventually point toward an extraordinary journey from Asia across a land bridge and into an America that had already forgotten what primates were. Today, we're going back to the tropical America buried beneath Wyoming and to the climate transformation that erased one of the continent's longest lasting mammal dynasties. If this is your kind of thing, hit like and subscribe. It costs nothing and it keeps this channel going. And drop a comment below. Are you watching this winding down for the night or watching this during your active day? Let's begin. Picture the continent before familiar seasons had taken shape, when North America rested beneath an atmosphere unlike anything living people have experienced. The chapter known as the Eocene Epoch stretched from about 56 million years ago until roughly 33.9 million years ago. Its name comes from an ancient Greek word meaning dawn, an appropriate title for an age when modern mammals were beginning to flourish across landscapes shaped by enduring warmth instead of winter. During the warmest part of that interval, known as the early Eocene climatic optimum, atmospheric carbon dioxide reached about 885 parts per million. That concentration created a greenhouse world with no close modern comparison. Average global temperatures remained about 18 degrees Fahrenheit warmer than those of the present day. This warmth extended across every season and every latitude, shaping an Earth where frozen landscapes had vanished entirely. There were no glaciers, no polar ice caps, and no permanently frozen ground. Oceans circulated through a planet wrapped in steady heat, allowing forests to spread across regions that today stand far outside the limits of subtropical vegetation. The transformation reached deep into the heart of North America. Forests extended from what is now Florida through Wyoming and Montana, continuing into lands that now belong to Canada. Instead of scattered woodlands separated by open country, an almost continuous canopy stretched across immense distances. Towering trees sheltered countless layers of vegetation below, creating a living roof where moisture lingered and fruiting plants flourished through much of the year. For animals adapted to life among branches, this landscape offered uninterrupted passage across an entire continent. Stone preserved the evidence with remarkable care. In Wyoming's Bighorn Basin, fossil pollen from palm trees reveals vegetation growing far beyond its modern range. The Green River Formation of southwestern Wyoming contains the remains of crocodilians, creatures unable to survive where yearly conditions fall below about 50 degrees Fahrenheit for long. Their presence shows that rivers and wetlands remained warm enough to support them throughout the seasons. Layers of ancient sediment also preserve figs, cattails, sycamores, and plant species now associated with forests of East Asia, assembling a botanical community that feels astonishing when compared with the dry country occupying the same ground today. Every fossil leaf, grain of pollen, and reptile skeleton contributes another brushstroke to this forgotten environment. Together, they describe broad floodplains crossed by winding rivers, shallow lakes edged with reeds, and forests rich with flowering plants. The landscape supported insects in extraordinary abundance, along with birds, reptiles, and mammals, filling ecological roles that depended upon stable warmth. Nothing about this setting resembled the windswept basins familiar across modern Wyoming. Into this flourishing world came the earliest primates. They encountered no struggling pockets of woodland pressed against an unforgiving climate. They stepped into forests already overflowing with fruit, leaves, shelter, and connected branches reaching from horizon to horizon. Every feature of the continent favored nimble animals that climbed, grasped, and leaped through the canopy. North America offered them space to spread, resources to thrive, and millions of years in which their story could unfold beneath leaves that rarely knew the touch of frost. Every long journey has a beginning, though the travelers rarely recognize the moment when the path first unfolds before them. For North America's earliest primates, that beginning can be traced with unusual precision to a brief interval in Earth's history called the Paleocene Eocene thermal maximum, around 56 million years ago. In the language of geology, where millions of years often pass like the turning of a page, this event arrived with startling speed. Across a span of only about 10,000 to 20,000 years, average global temperatures climbed by roughly 9 to 14 degrees Fahrenheit. Such a shift unfolded almost instantly on the geological clock. Researchers continue to debate the exact trigger. Some evidence points toward immense volcanic eruptions releasing carbon dioxide into the atmosphere. Other studies suggest large stores of methane escaped from the ocean floor as surrounding waters warmed. Both processes may have acted together, amplifying one another until the climate settled into an even warmer state than before. The changing atmosphere reshaped geography in ways that mattered just as much as the rising temperatures. Land bridges emerged across northern regions where sea levels and shifting coastlines exposed routes between continents. These passages did not resemble barren strips of exposed earth. Forest spread across them, joining distant lands beneath continuous tree cover. One corridor stretched through Beringia, linking what is now Siberia with Alaska. Another connected Greenland and Scotland across the North Atlantic. Small mammals that depended on branches instead of open ground suddenly found uninterrupted pathways extending across enormous distances. Those forests formed living corridors instead of obstacles. The same subtropical vegetation covering Wyoming reached far into northern latitudes, creating familiar habitat from one side of the world to the other. For an animal that spent its entire life climbing, grasping, and leaping among branches, the forest itself became the road. There was no need to understand continents or coastlines. Each new grove blended naturally into the next, carrying generations farther than any individual could ever know. The fossil record captures that movement with remarkable timing. In Wyoming's Bighorn Basin, the earliest documented North American primate appears within about 19,000 to 25,000 years after the warming began. Geologically, that arrival happened almost immediately. The little traveler bore the name Teilhardina. It weighed scarcely more than 1 ounce, scarcely larger than a mouse, with delicate hands and feet suited for rapid movement through branches. Far to the north, forests that would eventually vanish beneath colder climates offered shelter and food across regions that today appear unimaginable for tropical wildlife. Sharing this transformed continent was another newcomer, Cantius. Larger and sturdier than Teilhardina, it occupied a different place within the canopy, almost from the beginning. Its stronger frame allowed it to exploit resources beyond the reach of its tiny companion, establishing a lineage that would diversify across North America for millions of years. Their fossils appear near the dawn of this remarkable expansion, marking the first pages of a much longer history. Neither traveler crossed a frontier with intention. They followed shade, fruit, insects, and branches stretching onward through uninterrupted woodland. Each leap carried them into another familiar patch of forest, until familiar had become a new continent. North America welcomed them without barriers, offering a canopy that reached from Asia all the way to the forests of Wyoming, where their descendants would flourish for ages beyond memory. Among the earliest primates to establish themselves in North America, one animal became the foundation for nearly everything that followed. Its fossils appear in the oldest Wasachian rock layers, deposited at the boundary between the Paleocene and Eocene, placing its arrival at the very beginning of the continent's primate history. Known as Cantius, it stands as the oldest well-documented primate of modern appearance yet discovered in North America, already settled into its new home almost as soon as the warming world opened the northern forests. Compared with the tiny Teilhardina, Cantius occupied a noticeably different place in the forest. About the size of a small house cat, it carried a sturdier body that allowed it to exploit food and branches beyond the reach of its smaller companion. The contrast between them hints that North America's primate community began diversifying almost immediately. Different body sizes meant different opportunities, reducing competition while allowing several species to share the same living landscape. Although Cantius belongs within the primate family, it did not stand on the branch that eventually produced monkeys, apes, and humans. It belonged, instead, to the adapiforms, a group more closely related to the ancestors of today's lemurs and lorises. That relationship makes it a distant cousin in the broader primate family tree. Its existence reminds us that evolution rarely follows a single path. Many branches flourish together, each exploring its own way of living among the trees. Its teeth preserve one of the clearest clues to its daily life. The molars are low-crowned and well-suited for crushing soft, ripe fruit instead of grinding hard vegetation. Across the subtropical forests covering North America, flowering trees produced abundant seasonal harvests that rewarded agile climbers capable of reaching the canopy. Every bite reflects an environment where fruit remained plentiful enough to support specialized feeders over immense stretches of woodland. The skeleton tells an equally vivid story. The proportions of its arms and legs reveal an accomplished climber and leaper that spent nearly all of its life above the ground. Strong, grasping hands, flexible joints, and balanced limbs allowed confident movement through the middle levels of the forest. Branches formed its highways, feeding grounds, resting places, and escape routes. Descending to the forest floor likely happened only on rare occasions. As millions of years passed, Cantius did far more than survive. Multiple species emerged from this founding stock, spreading across broad regions of North America while adapting to different forests and ecological opportunities. Their success unfolded across a continent where no other primates competed for the same niches. The expanding family diversified into new forms, establishing the first enduring primate radiation the continent had ever known. Its earliest homeland, however, remains one of paleontology's enduring discussions. Some researchers favor an origin in Asia, followed by passage across Beringia. Others see stronger connections with European fossils, suggesting movement across the North Atlantic land bridge. A smaller group has proposed that the lineage may have evolved within North America itself, from ancestors not yet discovered. Fossils continue to refine these ideas without producing complete agreement. One conclusion stands beyond serious dispute. Before Cantius disappeared from the fossil record, North America's primates had already divided into several independent lineages, each adapting to different foods, different layers of the forest, and different ways of life. The first arrival had become the root of a thriving continental family, whose story was only beginning. Life in a flourishing forest rarely depends upon a single way of surviving. As the Middle Eocene unfolded, around 48 to 47 million years ago, North America's primates had expanded into a community where different species occupied different rhythms of the same woodland. They shared the trees without sharing every hour, every meal, or every branch. This gradual separation allowed an increasingly complex primate society to thrive across forests that stretched over much of the continent. One group belonged to the Adapiforms, descendants of the early pioneers already established across North America. These primates generally possessed larger bodies and spent their active hours beneath daylight, filtering through the canopy. Familiar names such as Cantius, Notharctus, and Smilodectes belonged to this branch. Their teeth reveal diets centered on fruit, tender leaves, and other plant foods gathered among the branches. Their larger size gave access to sturdy limbs supporting heavier animals while opening opportunities unavailable to their smaller relatives. Sharing those forests was a very different collection of primates known as the Ekgmowechashala. They were considerably smaller, with skulls dominated by remarkably large eye sockets. Although no living observer ever watched them moving through Eocene forests, their anatomy strongly suggests activity after sunset. Those oversized eyes gathered every available trace of light, much as a modern cat depends upon enlarged pupils to navigate after dusk. Insects formed an important part of their diet, rewarding alert hunters capable of locating tiny prey hidden among leaves and bark while much of the forest rested. These differences represented far more than variation in body size. Each lineage had developed its own solution to life within the same ecosystem. Daylight favored larger fruit and leaf specialists moving confidently through higher branches. Darkness rewarded compact insect hunters searching the lower canopy and tangled vegetation. Their schedules rarely overlapped enough to create constant competition, allowing many species to occupy one forest without exhausting the same food supplies. Paleontologists describe this arrangement as ecological partitioning, one of the clearest signs that an ecosystem has reached remarkable stability. Species divide available resources according to diet, activity, and location, reducing direct conflict while increasing the total number of animals the habitat can support. Such patterns appear wherever forests remain healthy across long stretches of evolutionary time, allowing numerous closely related species to coexist instead of forcing one another toward extinction. Modern examples still survive in a handful of places. The Congo Basin in Central Africa and the forests of Borneo shelter primate communities where different species occupy separate levels of the canopy, feed upon different foods, and remain active during different parts of the day. Their forests echo patterns established tens of millions of years earlier in North America. Wyoming, now associated with open country and broad skies, once supported ecological relationships strikingly similar to those found in the richest tropical forests remaining on Earth. The Omamiiforms also occupy a particularly meaningful place within the larger primate family tree. They belong to the haplorhine branch, the lineage that eventually produced tarsiers, monkeys, apes, and ultimately humans. Although these Eocene species left no direct descendants in North America, they shared fundamental evolutionary roots with the primates that continued diversifying across Africa and Asia. The forests of Eocene North America therefore held far more than an assortment of unfamiliar mammals. Their branches supported close relatives of lineages that would continue evolving for millions of years beyond the continent's own primate history, carrying forward traits that eventually shaped the broader story of our own family tree. Among all the primates known from North America's distant past, one stands apart through the extraordinary amount of evidence it left behind. Fossils preserve enough of its skeleton, skull, teeth, and even the shape of its brain case that scientists can reconstruct its appearance and way of life with unusual confidence. That animal is Notharctus, one of the clearest windows into a primate world that flourished across the Eocene forests. Its scientific story unfolded over many generations of research. Joseph Leidy first described Notharctus in 1870 from fragmentary fossils, recognizing that the scattered bones represented something remarkable. Decades later, Walter Granger's excavations in Wyoming's Bridger Basin uncovered far more complete material, allowing the animal to emerge from isolated fragments into a recognizable creature. The most detailed early reconstruction arrived in 1920, when William King Gregory published a landmark study through the American Museum of Natural History, carefully comparing every available bone with living primates. The finished portrait revealed an agile climber about 15 to 18 inches long, weighing roughly 4 to 7 pounds. Its proportions resembled those of a small house cat, while its face and body carried a striking resemblance to a modern lemur. Gregory observed that every major limb bone closely matched corresponding structures in living lemurs, supporting the conclusion that Notharctus moved through the forest by climbing and leaping from branch to branch with practiced ease. Its skull measured only about 2 inches in length, yet every feature reflected a life spent among trees. Long canine teeth projected from the jaws, while a pronounced muzzle extended slightly beyond the face, though remaining somewhat shorter than that of many living lemurs. Forward-facing eyes provided overlapping fields of vision that improved depth perception during leaps through the canopy. Both hands and feet possessed an opposable first digit, creating the firm grasp that defines primates and allows secure movement across branches of every thickness. Its feeding habits matched the rich environment surrounding it. The teeth indicate a diet centered on fruit and leaves, supplemented at times by insects gathered from bark or foliage. Such flexibility allowed Notharctus to exploit many food sources without relying upon only one. Across forests that remained productive throughout the year, ripe fruit, tender leaves, and small animals offered dependable nourishment without the severe seasonal shortages experienced in later climates. The geographic reach of Notharctus was equally impressive. Fossils have been recovered from Colorado, Utah, Wyoming, New Mexico, Nevada, and Texas, demonstrating that it occupied an immense network of connected forests extending across much of western North America. This distribution reflects a widespread and successful lineage instead of a localized population restricted to one valley or watershed. Wyoming's Bridger Basin has proven especially generous. Hundreds of Notharctus specimens have emerged from its rock layers, including skulls, isolated teeth, and nearly complete skeletons. Few fossil primates anywhere in the world are represented by such abundant material from a single genus. Each discovery refines details of anatomy, growth, and variation, turning scattered bones into one of paleontology's most complete portraits of an early primate. The fossil record places Notharctus between about 50 million and 45 million years ago, giving the genus a documented history spanning roughly 5 million years. That interval is about 16 times longer than the entirety of recorded human history. Across those countless generations, this adaptable climber remained one of the defining inhabitants of North America's forest canopy, leaving behind a legacy preserved with remarkable clarity in stone. Sometimes the most revealing fossil is not a bone itself, but the space hidden inside it. A skull can preserve delicate impressions left by the brain that once filled it, creating a natural mold of an organ long vanished. For generations, those impressions remained beyond scientific reach. Then, in 2016, researchers from Duke University and the University of Toronto used advanced computed tomography scanning to look inside fossil skulls of Notharctus, tenebrosus, and Smilodectes gracilis, rebuilding their brains as detailed digital models without disturbing the fossils themselves. The resulting reconstructions were known as virtual endocasts, three-dimensional representations created from the inner surfaces of the skull where the brain had rested millions of years earlier. Instead of relying upon speculation or rough comparisons with living animals, researchers could examine the proportions of different brain regions with remarkable precision. Those ancient skulls, preserved through unimaginable spans of time, had carried a neurological record waiting for technology capable of reading it. The reconstructed brains revealed patterns that distinguished these primates from many other mammals living during the same period. One feature stood out immediately. The visual cortex, responsible for processing information gathered through the eyes, occupied a larger proportion of the brain than expected for mammals of comparable body size. At the same time, the olfactory bulbs, devoted to interpreting scents, were noticeably reduced. Evolution had already begun shifting valuable neural space away from smell and toward vision. That exchange carried profound consequences for life among branches. Forward-facing eyes already supplied overlapping fields of vision, allowing depth perception impossible with widely separated eyes. Enlarging the visual regions of the brain strengthened the ability to interpret those signals rapidly and accurately. For an animal moving through a layered canopy, every leap depended upon judging distance with remarkable precision. Miscalculations could end in injury or death, while accurate vision transformed an intricate network of branches into dependable pathways connecting food, shelter, and companions. Although these adaptations served immediate needs within the forest, they also formed part of a much longer evolutionary direction. The same neurological organization later supported increasingly sophisticated visual processing in other primates. Recognizing subtle facial expressions, distinguishing familiar individuals after long absences, interpreting complex social interactions, and eventually supporting the foundations required for language, all depended upon brains, placing growing emphasis on vision. Those later achievements remained unimaginably distant, yet some of their earliest neurological groundwork had already appeared. The Wyoming primates, therefore, occupy an important place in the broader history of cognition. Their lineage eventually disappeared from North America, but the pattern recorded within their skulls did not vanish with them. Similar neurological changes unfolded among related primates living across Africa and Asia. Separate populations followed comparable evolutionary directions, each refining the balance between perception, movement, and social awareness through countless generations. The disappearance of one branch never erased the larger experiment already underway. Evolution continued exploring the possibilities opened by improved vision, more flexible hands, and increasingly capable brains. Other primates survived climatic change, spread into new habitats, and diversified into forms unlike anything present during the Eocene. Millions of years later, descendants of those surviving lineages developed the curiosity and technology to peer inside fossil skulls using computed tomography scanners, reconstruct brains that had rested in stone since deep time, and recognize within them the earliest outlines of a story still unfolding in every living primate today. Within the same forests where Notharctus traveled through the canopy, another primate followed a neighboring path without truly competing for the same rewards. Fossils of Smilodectes gracilis lie preserved in the very same rock layers of Wyoming's Bridger Basin, placing both animals in the same woodland at the same moment in deep time. Their skeletons tell the story of neighbors whose lives overlapped across countless generations, each shaped by a different solution to living among the trees. At first glance, the distinction appears modest. Smilodectes weighed about 4.4 pounds, making it somewhat smaller than Notharctus. In a complex ecosystem, however, even subtle differences can influence how animals move, feed, and avoid competition. Evolution often works through adjustments that seem minor when viewed in isolation, yet those adjustments become powerful when repeated across millions of years. The clearest difference rested within the teeth. The molars of Smilodectes carried pronounced shearing crests, structures especially effective for slicing leaves. These features identify it as a dedicated folivore, an animal relying primarily upon foliage instead of ripe fruit. Nearby, Notharctus continued feeding more heavily on fruit while supplementing its diet with other available foods. The two primates occupied the same forests, climbed many of the same trees, and shared the same climate, yet they harvested different parts of the vegetation surrounding them. That separation illustrates one of ecology's most important principles, known as niche partitioning. Species living side by side avoid exhausting identical resources by dividing the environment into distinct ecological roles. One animal specializes in food, another rarely uses. Another occupies a different layer of vegetation or becomes active during another portion of the day. Such divisions reduce direct competition while allowing greater diversity to flourish within the same landscape. Modern tropical forests demonstrate this principle with remarkable clarity. In parts of Africa, dozens of primate species may inhabit a single rainforest, each exploiting a particular combination of food, height within the canopy, or daily activity. The result is not disorder but balance, with many closely related animals sharing one habitat because their ecological roles overlap only slightly. The Eocene forests of North America achieved a comparable level of organization long before those modern forests developed their present communities. Evidence from the inside of the skull strengthens this picture. Digital endocasts, created through computed tomography scanning, reveal that Smilodectes possessed the same broad neurological pattern observed in Notharctus. Brain regions devoted to vision were relatively enlarged, while those dedicated to smell had become reduced. This shared arrangement demonstrates that the neurological transformation described earlier extended across the adapiform lineage instead of appearing within only a single species. Closely related primates, despite differing diets, were advancing along the same evolutionary direction. The fossil record shows that Smilodectes disappeared around 45 million years ago, close to the same interval when Notharctus also vanished. Their absence did not coincide with an abrupt collapse. Gradual climatic cooling had begun reshaping northern forests, slowly reducing the warm habitats upon which these specialized primates depended. The earliest changes unfolded almost unnoticed across generations, altering the edges of the continent before reaching its interior. Their departure marked the opening notes of a longer transformation. The forests still endured, and primates still remained elsewhere, yet the conditions that had supported this remarkably balanced community were beginning to shift. Long before the final chapters arrived, the landscape had already started composing a different future. A civilization does not need cities or monuments to leave a lasting legacy. Sometimes its endurance is measured in generations so numerous that individual species become only brief chapters within a much greater story. For North America's primates, that story stretched across roughly 20 million continuous years, from their arrival around 56 million years ago until their disappearance near 34 million years ago. During that immense span, primates remained an established part of the continent rather than temporary visitors passing through. The scale of that persistence becomes clearer when placed beside our own history. Modern Homo sapiens have existed for only about 300,000 years. The primate lineage that occupied North America endured for roughly 67 times longer than our own species has yet lived. Entire cycles of evolution unfolded, while those forests continued supporting generations of climbing mammals whose descendants changed gradually with the passing of countless ages. Their community never remained frozen in time. Evolution continued shaping new forms as older ones faded from the landscape. Early pioneers, such as Cantius, eventually disappeared, giving way to well-known adapiforms including Notharctus and Smilodectes. Later, different omomyiform species assumed greater prominence as environments slowly shifted. Individual genera rose and vanished, yet primates themselves never disappeared from the continent during those millions of years. The lineage remained remarkably continuous, even as its members changed. Those primates shared their forests with an extraordinary collection of animals. Small early horses, known as eohippus, little larger than modern foxes, moved through open patches of vegetation. Primitive tapirs and early camels wandered nearby, bearing only distant resemblance to their modern descendants. Ancient crocodilians occupied rivers flowing across what is now Wyoming, while giant members of the boa family hunted within dense vegetation. Towering titanotheres, distant relatives of rhinoceroses, gradually evolved into enormous herbivores approaching the size of elephants. Together they formed communities of remarkable richness across the continent. This was far from a simple world, recovering after the age of dinosaurs. Food webs extended through rivers, forests, wetlands, and open woodlands, connecting predators, herbivores, insects, reptiles, and mammals in intricate ecological relationships. Primates occupied one enduring thread within that network, woven into ecosystems that supported astonishing biological diversity. Their role had become established through millions of years of adaptation rather than recent arrival. The rocks preserving this history are equally remarkable. The Bighorn Basin, the Bridger Basin, and the Green River Formation contain fossil sequences so complete that paleontologists can follow evolutionary change almost layer by layer. As one horizon gives way to another, subtle differences appear in teeth, skulls, and skeletons, allowing researchers to observe populations gradually shifting through deep time instead of relying upon isolated snapshots. Few places on Earth preserve early primate evolution with such continuity. Across those countless generations, stability became the defining feature of North America's primate history. Forests changed, climates fluctuated, and individual species emerged before yielding to successors, yet the larger community persisted with remarkable resilience. Such long-lived ecological success might appear almost permanent when viewed from the perspective of a single lifetime. Even through the perspective of many millions of years, the pattern remained astonishingly consistent. Then, almost beyond ordinary perception, the conditions supporting that stability began to drift. The first signs did not appear in North America itself. They emerged far beyond the continent, where changes unfolding elsewhere would eventually reshape forests that had endured for 20 million years. The turning point in North America's primate story began far beyond the forests they called home. No warning appeared first in Wyoming's valleys or along the rivers winding through the continent. The first movement unfolded on the opposite side of the planet, in a place now defined by ice, although it had once looked astonishingly different. During most of the Eocene, Antarctica supported temperate forests, flowing rivers, and a climate mild enough for diverse plants and animals to flourish across its landscape. Its transformation began through the slow movement of continents. As Antarctica and South America continued drifting apart, the ocean passage separating them gradually widened. This opening, known as the Drake Passage, did not reshape the planet overnight. Across millions of years, it expanded until seawater could circulate freely around Antarctica without interruption from neighboring landmasses. That seemingly gradual geographic change altered one of Earth's most important climate systems. Around 34 million years ago, the widening passage reached a critical stage. Ocean currents reorganized into a continuous flow encircling Antarctica from west to east. This circulation became known as the Antarctic Circumpolar Current. For the first time, warm tropical waters could no longer reach the southern continent efficiently. Antarctica became increasingly isolated from the heat that had moderated its climate throughout much of the Eocene, allowing temperatures to decline across the region. Cooling gradually strengthened until ice accumulated faster than it melted. Around 33.55 million years ago, scientists identify a major climatic transition known as the Oi-1 glaciation. The name comes from changes in oxygen isotope ratios preserved within microscopic shells buried in ocean sediments around the world. Those chemical signals record the rapid expansion of permanent Antarctic ice, marking the point when a self-sustaining continental ice sheet had become established. As enormous volumes of water became trapped within growing glaciers, global sea levels fell dramatically. Estimates suggest a decline of roughly 165 to 230 feet. Coastlines shifted outward, shallow seas retreated, and weather patterns responded to a planet whose balance had fundamentally changed. The growing ice sheet also reflected increasing amounts of sunlight back into space instead of absorbing that energy. This created a powerful climatic feedback, reinforcing cooling that had already begun through changes in ocean circulation. The atmosphere was changing as well. Across this same interval, carbon dioxide concentrations declined substantially. Evidence gathered from multiple geological records indicates values falling from roughly 885 parts per million to about 560 parts per million. With less carbon dioxide retaining heat and Antarctica reflecting greater amounts of incoming sunlight, global temperatures continued moving toward a cooler state that extended well beyond the polar regions. North America did not escape these changes. The continent had already experienced a gradual cooling trend during the late Eocene, yet the reorganization of Earth's climate system pushed those existing trends beyond an important threshold. Forests that had expanded across enormous regions began contracting as temperatures continued falling. Habitats that had supported stable primate communities for millions of years slowly became less extensive, especially across northern areas where environmental conditions shifted first. Nothing about this transformation resembled a sudden catastrophe visible within a single lifetime. It unfolded through the patient rhythms of geology, guided by drifting continents, changing oceans, growing ice, and an atmosphere settling into a different balance. Yet, those distant events on Antarctica reached across the globe, altering the future of forests thousands of miles away and setting the stage for one of North America's longest lasting lineages to approach its final chapter. The end arrived without a single defining day. No crater marked the landscape, no curtain of ash settled across the continent, and no sudden collapse erased North America's primates from existence. Their disappearance unfolded through a sequence of gradual changes, each one small enough to seem almost insignificant on its own. Across thousands of generations, those changes accumulated until the world supporting a flourishing primate community no longer existed. As carbon dioxide levels continued falling, the atmosphere retained less heat. Seasons that had once remained mild grew increasingly variable. Winters lengthened and became colder across regions that had experienced warm conditions for roughly 20 million years. Frost reached forests where it had once been uncommon, introducing a rhythm entirely unfamiliar to ecosystems shaped by millions of years of subtropical stability. The climate was rewriting the rules under which every plant and animal had evolved. For animals living among branches, the challenge extended far beyond lower temperatures. Primates are remarkably adaptable in many ways, yet they depend upon the structure and productivity of forests. When repeated frost reached broad areas of woodland, trees lost leaves, fruiting cycles became disrupted, and insect populations declined during the coldest parts of the year. A canopy that had once supplied food through every season could no longer provide continuous nourishment. The difficulty lay within the changing forest itself, whose seasonal shortages grew more severe with each passing age. Plants recorded this transformation with remarkable fidelity. Fossil pollen preserved within ancient sediments reveals tropical and subtropical species gradually retreating southward as climates cooled. Their place was increasingly occupied by deciduous trees, species adapted to surviving cold winters by shedding their leaves. During those leafless months, branches stretched across the sky without the dense vegetation that had once formed uninterrupted pathways through the forest. For fruit-eating and leaf-eating primates, entire seasons now offered little nourishment and diminishing shelter. The broader landscape changed alongside the vegetation. Dense forests gave way to more open woodlands across many regions. As cooling continued, expanding grasslands occupied areas once covered by trees. Such environments created opportunities for some mammals while steadily removing the habitat required by animals specialized for life above the ground. A primate built for climbing cannot replace a forest with an open plain. Without connected branches overhead, movement, feeding, resting, and protection all become increasingly difficult. Each shrinking forest left surviving populations more isolated than before. Woodland fragments, separated by growing stretches of unsuitable terrain, reduced opportunities for movement between groups. Smaller populations became increasingly vulnerable to ordinary challenges such as seasonal shortages and natural variation in birth rates. None of these pressures acted alone. Together, they formed a persistent pattern that gradually narrowed the range where North America's primates could continue living successfully. The fossil record offers no evidence of a dramatic final refuge where the last survivors gathered before disappearing. There was no single valley preserving the closing chapter of a once widespread lineage. Instead, populations faded from one region after another as suitable habitat continued contracting. Forest edge followed forest edge until each remaining population occupied a smaller world than the generation before. By the time the process reached its conclusion, the disappearance seemed almost inevitable, though nothing about it had been sudden. The dynasty that had endured for roughly 20 million years yielded to countless small losses accumulating across immense stretches of time. Its ending resembled the steady retreat of a shoreline, measured not by one great event, but by the patient rhythm of a changing earth. The rocks of Europe preserve one boundary so striking that it earned its own name. In 1910, Swiss paleontologist Hans Georg Stellen examined fossil sequences spanning the close of the Eocene and recognized a pattern too abrupt to ignore. He called it the Grande Coupure, a French phrase meaning the Great Cut. The name captured exactly what the sediments revealed, a point where one long-established mammal community disappeared and another emerged with startling speed. Unlike many evolutionary transitions, this boundary does not appear as a slow blending of old and new faunas. Layer after layer records a thriving collection of mammals, then another layer presents a dramatically different assembly. Entire groups that had flourished for millions of years are absent, replaced by newcomers, adapted to cooler and more seasonal conditions. In geological history, such an interval is exceptionally sharp, resembling a clean line separating two chapters rather than a gradual fading between them. This event corresponds with the boundary between the Eocene and Oligocene epochs, approximately 33.9 to 33.5 million years ago. Although the name originated from European discoveries, the transformation itself extended far beyond a single continent. Geological evidence from widely separated regions demonstrates that Earth's ecosystems were responding to the same broad climatic forces, reshaping oceans, atmosphere, and vegetation across the globe. The scale of biological turnover remains extraordinary. Within roughly 1 million years surrounding this boundary, scientists estimate that about half of all mammal genera disappeared worldwide. Measured against the immense span of geological time, this represented a remarkably rapid restructuring of life on land. Countless evolutionary lineages that had persisted through much of the Eocene reached their conclusion within what, to geology, amounted to a brief interval. Europe displayed the change with particular clarity. Mammal communities that had evolved in relative isolation over millions of years vanished from the fossil record. Soon afterward, species originating in Asia appeared within the same rock sequences, indicating that changing climates and shifting habitats opened migration routes previously unavailable. The biological character of an entire continent was reorganized in a comparatively short period. Across Asia, paleontologists recognize a closely related episode known as the Mongolian remodeling. Although preserved within different landscapes, its timing parallels the Grande Coupure and reflects many of the same ecological adjustments. Mammal communities reorganized as environments became cooler and drier, demonstrating that the forces driving these changes operated across much of the northern hemisphere instead of remaining confined to one region. North America's fossil record presents a somewhat different appearance. No single rock layer forms an equally dramatic dividing line, yet the overall outcome closely mirrors events elsewhere. Animals associated with warm subtropical forests gradually yielded to species better suited for open woodlands, expanding grasslands, and increasingly seasonal climates. The transition unfolded across many fossil sites, each recording another part of the same planetary transformation. Among the mammals affected on every continent were the primates. Fossil sequences preserving sufficient detail repeatedly show their decline near this boundary. Some regions lost entire lineages, while others retained only distant relatives before they too disappeared. Their long history, extending through millions of years of favorable conditions, could not withstand a world reorganizing around colder seasons and changing forests. Half of all mammal genera vanished within a geological moment. For human experience, that interval remains almost unimaginably long. Even so, the rocks preserve unmistakable evidence that Earth's living communities can sometimes change with surprising speed, replacing one enduring world with another before the planet has finished turning a single page of its deeper history. Some chapters of Earth's history are written in fossils, others are written by their complete absence. After roughly 34 million years ago, the North American record preserves one of those extraordinary absences. The evidence does not become uncertain or fragmentary. It does not fade gradually into scattered discoveries. Across the continent, the record of primates comes to a complete halt. That conclusion rests upon more than a century of careful excavation. Paleontologists have examined Oligocene deposits from an impressive range of fossil localities, including the Badlands of South Dakota, the White River Formation of Nebraska, the John Day Formation of Oregon, and rich exposures throughout Wyoming, Colorado, and Montana. These sites have produced thousands of mammal fossils representing predators, grazers, burrowing species, and climbing animals. Together, they preserve one of the most thoroughly studied windows into North America's changing ecosystems. Within that enormous collection, one kind of fossil never appears. Researchers have recovered no primate teeth, no jaw fragments, no isolated limb bones, and no skulls belonging to the descendants of the lineages that had flourished throughout the Eocene. Every excavation adds new information about the mammals that survived the climatic transition, yet none has revealed evidence that even a small remnant population remained anywhere on the continent. For approximately 4.5 million years, North America existed without primates. The absence lasted longer than the entire span, separating modern humans from the last common ancestor shared with gorillas. Such a comparison places the gap into a scale that is easier to appreciate. A lineage that had occupied the continent continuously for about 20 million years disappeared so completely that millions more years passed without leaving even a single confirmed trace behind. The animals expanding during this interval represented a different ecological world. Horses increased in size and became better adapted for traveling across more open country. Early camels diversified into forms unlike those of the Eocene, while primitive rhinoceroses spread through habitats shaped by cooler climates and changing vegetation. These mammals were successful within landscapes dominated by woodlands and expanding grasslands, environments rewarding endurance, grazing, and efficient movement across open ground. None of these species filled the ecological role once occupied by forest primates. Their bodies were not designed for grasping branches overhead or moving through connected canopies. Their diets reflected different opportunities, and their social lives developed under different environmental pressures. The disappearance of primates left no direct replacement because the forests supporting that distinctive way of life had themselves been transformed beyond recognition. From a scientific perspective, this prolonged absence carries enormous significance. Fossil evidence is often evaluated cautiously because missing discoveries can reflect incomplete preservation. Here, the pattern extends across many formations, countless excavations, and millions of years. The consistency of that absence becomes evidence in its own right. It indicates that North America's primates had not merely become uncommon, they had vanished completely, leaving no isolated refuge in warmer southern forests and no overlooked population lingering beyond the reach of changing climates. The continent remained without primates for ages beyond ordinary imagination. Then, within rocks dating to approximately 29.5 million years ago from western Nebraska, paleontologists encountered a discovery that interrupted this long emptiness. After millions of years without a single trace, something unmistakably primate appeared once again, arriving in a land where its relatives had long since disappeared. Every so often, a fossil appears that seems to belong to another story altogether. During the 1960s, paleontologists working the fossil-rich sediments of western Nebraska uncovered a single molar from rocks dating to the Oligocene. The age of those deposits was well established. They had formed millions of years after North America's primates had disappeared from the fossil record. By every expectation built from decades of research, no primate should have been present there. The tooth unmistakably belonged to a primate. Its discovery did not inspire immediate celebration. Instead, it created uncertainty. The extinction pattern across North America had appeared exceptionally complete, reinforced by extensive collections from numerous formations and supported by similar evidence from elsewhere. A primate emerging from younger Oligocene sediments challenged an understanding that had seemed firmly established. The specimen raised a question that no one could answer with confidence. As additional study continued, the mysterious animal received the name Ekgmowechashala, derived from a Sioux language phrase commonly translated as little cat man. The unusual name reflected an equally unusual animal. It was small and unquestionably primate, yet it resisted placement within any familiar North American lineage. Its features hinted at relationships beyond the continent's known evolutionary history, while refusing to fit comfortably into existing classifications. The mystery deepened as more material came to light over the following decades. Additional teeth and fragments of jaws emerged from Nebraska, confirming that the first discovery had not been an isolated accident. Later excavations recovered further specimens in Oregon, again from Oligocene rocks deposited during the long interval when North America was believed to have remained completely without primates. Each new fossil strengthened the reality of the animal while making its presence increasingly difficult to explain. Careful examination of its anatomy complicated matters further. Ekgmowechashala did not resemble a surviving member of the primates that had flourished before the climatic transition. It lacked the distinctive characteristics expected if it had simply descended from forms such as Notharctus or the ammomniform primates that once inhabited Eocene forests. Its teeth displayed specialized features, suggesting an evolutionary history that had unfolded elsewhere or along a branch still hidden from the fossil record. Two broad explanations gradually emerged. One possibility proposed that a tiny population of North American primates had somehow escaped extinction within an isolated refuge. Hidden in a region where suitable forest persisted, these survivors might have remained undetected for approximately 4.5 million years before finally appearing again in the fossil record. Such a scenario demanded a remarkable stretch of invisible history, requiring an entire lineage to leave no trace across millions of years despite extensive fossil sampling. The second possibility pointed beyond North America altogether. Perhaps Ekgmowechashala represented an immigrant whose ancestors had evolved on another continent before eventually reaching the Great Plains. If that interpretation proved correct, the fossil would mark a return rather than a survival, introducing a newcomer into a landscape that had long since lost its original primates. Yet, no convincing ancestral population had been identified, and no migration route could be demonstrated with certainty. For roughly 60 years, the evidence balanced between those competing ideas. The fossils were genuine, their geological age remained unquestioned, and the animal itself refused to reveal its origins. It stood within museum collections as one of paleontology's most intriguing puzzles, waiting for discoveries beyond North America to illuminate a journey the continent's own rocks could not explain. For decades, the puzzle remained exactly where it had begun. The unusual primate from Nebraska refused to fit into any established branch of the evolutionary tree, and each new study seemed only to sharpen the uncertainty. From the 1960s into the early 2020s, generations of paleontologists examined the available evidence, testing one explanation after another. Despite their efforts, the origin of Ekgmowechashala remained one of the most persistent, unsolved questions in North American primate research. One possibility suggested that the animal represented the final descendant of North America's ancient primates. According to this idea, a small population had somehow survived the climatic collapse that erased every known Eocene lineage from the continent. Hidden within an isolated pocket of suitable habitat, these survivors would have continued evolving for approximately 4.5 million years before finally leaving fossils in Oligocene rocks. The hypothesis offered an appealing explanation for the animal's unexpected presence, yet it carried a substantial anatomical difficulty. Its teeth and jaws differed too greatly from those of known Eocene primates. Researchers compared the fossils with Notharctus, the Omomiiform primates, and every other established North American lineage, searching for a convincing ancestral connection. None proved satisfactory. The anatomical differences extended beyond what could comfortably be explained by ordinary evolutionary change within a hidden population. Too much evolutionary history appeared to be missing between the older fossils and the mysterious newcomer. The alternative interpretation proposed that Ekgmowechashala had arrived from another continent. That possibility solved one problem while creating another. If the animal had immigrated into North America, where had it originated? Paleontologists searched fossil collections from Europe and Asia for a close relative that could bridge the gap, yet none emerged. The evolutionary tree ended almost as soon as it began. Ekgmowechashala possessed a documented existence, but its ancestry seemed to vanish beyond the reach of known fossils. The uncertainty reached even deeper than geography. Into the early years of the 21st century, some researchers questioned whether the animal belonged within the primate order at all. Certain features resembled those of primates, yet similar characteristics have evolved independently in unrelated mammals through convergent evolution. That process repeatedly demonstrates how animals adapting to comparable ecological challenges can develop strikingly similar anatomy despite sharing no close ancestry. If convergent evolution explained the Nebraska fossils, the entire discussion about surviving or immigrating primates would rest upon an incorrect assumption. Gradually, additional anatomical studies shifted opinion. Comparisons of dental structure and jaw morphology increasingly supported the interpretation that Ekgmowechashala truly was a primate. By the early years of the 21st century, many specialists accepted that conclusion, although important uncertainties remained. Agreement about its identity did not reveal where it had evolved, who its closest relatives had been, or how it reached a continent that had remained without primates for millions of years. The search for answers eventually extended far beyond North America. The evidence required to resolve the mystery was not waiting beneath the Great Plains or hidden within another western basin. It rested nearly 10,000 miles away, inside rocks exposed across southern China. There, the remains of a small primate that had died roughly 30 million years ago preserved the missing chapter, although no scientist had yet recognized the remarkable connection linking those distant fossils to the lonely teeth discovered decades earlier in Nebraska. Scientific mysteries sometimes endure because an essential piece of evidence has not yet been discovered. For more than 60 years, Ekgmowechashala occupied that uncertain place. Its fossils were real, its age was secure, and its identity had gradually become accepted, yet its ancestry remained concealed. The answer finally emerged in November of 2023, when an international team published a study that transformed one of North American paleontology's longest-running debates into a remarkably coherent story. Researchers from the University of Kansas joined colleagues from the Institute of Vertebrate Paleontology and Paleoanthropology in Beijing to examine a newly discovered primate from the Nadu Formation in the Guangxi-Zhuang Autonomous region of southern China. The fossil came from the late Eocene, making it older than every known specimen of Ekgmowechashala recovered in North America. Its age alone made the discovery important, but its anatomy proved even more revealing. The newly recognized species received the name Paleohodites, meaning ancient wanderer. Detailed phylogenetic analysis compared its skeletal characteristics with those of numerous fossil primates across Asia and North America. The results consistently placed Paleohodites as the closest known relative or sister taxon of Ekgmowechashala. Both belonged within a broader radiation of southern Asian adapiform primates that also included genera such as Getanthropus, Muangthenhinius, and Bugtylimer. Their family relationships no longer ended abruptly in Nebraska. The missing branch had finally appeared. That relationship reshaped the entire narrative. Ekgmowechashala was not the lingering survivor of North America's vanished Eocene primates. Its lineage had never experienced the extinction that eliminated those earlier animals. While forests disappeared across higher latitudes and North American primates faded from the continent, the ancestors of Ekgmowechashala continued evolving thousands of miles away in southern Asia, separated from those events by geography as well as climate. Southern Asia had served as an environmental refuge during one of Earth's most significant climatic transitions. Its lower latitude preserved warmer temperatures and forests capable of sustaining primates long after similar habitats had contracted elsewhere. Conditions remained comparatively stable, while ecosystems farther north underwent sweeping ecological change. For certain primate lineages, that refuge provided the opportunity to persist, diversify, and continue their evolutionary history beyond the boundary that ended so many related groups. Only much later did one branch begin moving toward North America. Around 29.5 million years ago, Ekgmowechashala, or an immediate ancestor, crossed the Beringian land connection linking Asia and North America. That corridor had previously carried other mammals between the continents, including the earliest primates, to reach North America millions of years before. This later migration followed the same general pathway, although it entered a continent transformed almost beyond recognition. The landscape awaiting these immigrants differed profoundly from the warm forests where their lineage had endured. Cooler seasons, expanding open habitats, and increasingly dry environments dominated much of North America. Ecologically, it represented unfamiliar territory for descendants of primates shaped within sheltered southern forests. Every aspect of their inherited adaptations had evolved under conditions unlike those they now encountered. Yet the fossils demonstrate that the journey succeeded, at least for a time, against expectations formed before the discovery of paleohodites. This immigrant lineage established itself within North America after millions of years without native primates. The Chinese fossil did more than identify a close relative. It revealed that one small traveler had reopened a chapter of continental history long believed to have ended forever. Some fossils seem to vanish from history, only to appear again after an interval so immense that their return almost defies expectation. Paleontologists describe such lineages as Lazarus taxa, borrowing the name from the biblical account of Lazarus, who was restored to life after 4 days. Within geology, however, the interval is measured on an entirely different scale. The disappearance lasts not for days, but for millions of years, preserved as an uninterrupted gap in the fossil record before the lineage unexpectedly appears once more. The term does not suggest resurrection, nor does it imply that evolution paused and somehow began again. A Lazarus taxon reflects the limits of the fossil record itself. Animals can continue living in places where suitable rocks have not survived, where sediments remain buried, or where paleontologists have not yet searched. During those missing chapters, the lineage continues evolving beyond human observation. Only when fossils are eventually discovered does the apparent disappearance resolve into a story of survival rather than extinction. That explanation fits Ekgmowechashala remarkably well. While North America's primates vanished during the climatic upheaval marking the close of the Eocene, its own lineage persisted in southern Asia. Forests there remained favorable enough to support adapiform primates, while ecosystems across higher latitudes underwent profound ecological change. For approximately 4.5 million years, those distant populations continued their evolutionary journey, entirely absent from the North American fossil record, yet never truly gone from Earth. Eventually, descendants of that surviving lineage moved eastward across the Beringian land connection and entered North America once again. Their appearance in Nebraska, approximately 29.5 million years ago, represented far more than the arrival of another mammal species. It demonstrated that the continent's long interval without primates had finally ended, not through the survival of ancient North American forms, but through the arrival of immigrants whose ancestors had weathered the climatic crisis elsewhere. The significance of that return extends into the geological timescale itself. The presence of Ekgmowechashala helps define the beginning of the Araucarian North American land mammal age, an interval recognized through characteristic fossil communities preserved across the continent. Among the many mammals marking that transition, this small primate occupies a particularly memorable place because its appearance resolves an absence stretching across millions of years. A single lineage emerging from the rocks contributes to identifying an entirely new chapter in North America's fossil history. Its story also marks the closing pages of another remarkable narrative. After Ekgmowechashala, the North American fossil record contains no evidence of non-human primates for an extraordinarily long span. The continent would remain without them until members of our own species eventually crossed Beringia between approximately 14,000 and 20,000 years ago, bringing primates back once more through the same northern gateway. Viewed across the sweep of geological history, the pattern possesses an elegant symmetry. The earliest primates reached North America by way of Beringia roughly 56 million years ago. The final known non-human primate also arrived by crossing that same connection after evolving in Asia. Much later, human beings followed the identical corridor into the continent. Across 56 million years, the same landscape served three separate migrations, linking distant eras through a narrow bridge that repeatedly connected continents, ecosystems, and the long history of the primate family. The image of Ekgmowechashala that scientists can reconstruct remains necessarily incomplete. Unlike famous fossil species preserved as nearly whole skeletons, this primate is known primarily through its teeth and fragments of its jaws. Those small pieces carry an extraordinary amount of information, yet they also define the limits of what can be said with confidence. Many details of its appearance, movement, and daily behavior remain beyond the reach of present evidence. Its size is among the clearer conclusions. Comparisons with living and fossil primates indicate an animal roughly between a large rat and a small squirrel in body mass. It was considerably smaller than earlier North American adapiforms, such as Notharctus. That reduced size reflects both its separate evolutionary history in southern Asia and the environmental conditions under which its lineage persisted, after many related forms had disappeared elsewhere. The teeth provide additional clues about its way of life. Their shape and wear patterns suggest a diet centered largely on fruit, supplemented by insects when available. Such feeding habits fit comfortably within what is known about adapiform primates, although Ekgmowechashala probably occupied forests offering fewer, abundant resources than those enjoyed by its distant Eocene relatives. Seasonal variation and cooler climates likely demanded greater flexibility in locating food throughout the year. Evolutionarily, it belonged to the same broad adapiform radiation that included North American genera such as Notharctus and Smilodectes. Their relationship, however, was no simple continuation of the continent's earlier history. After the North American adapiforms disappeared during the climatic transition at the close of the Eocene, the ancestors of Ekgmowechashala continued evolving independently in southern Asia. Millions of years passed before one branch of that surviving lineage eventually crossed Beringia and returned to a continent where its distant relatives had long since vanished. The North America it entered bore little resemblance to the lush environments occupied by those earlier primates. Much of the Great Plains had become cooler, drier, and increasingly seasonal. Expanding grasslands steadily replaced forests that once stretched across broad regions of the continent. Woodlands still persisted in places, yet they existed within landscapes undergoing continuing ecological transformation. These were the same changes that had contributed to the disappearance of the continent's original primate communities. Exactly how Ekgmowechashala navigated those altered environments remains uncertain. The available fossils reveal almost nothing about its arms, legs, hands, or feet, leaving its climbing abilities open to interpretation. Scientists cannot yet determine whether it spent most of its time in trees, divided its activities between branches and the ground, or adopted behaviors unlike those of its earlier relatives. Its social organization is equally difficult to reconstruct. Whether individuals lived alone, in family groups, or within larger communities, remains hidden alongside the missing portions of its skeleton. Even with those uncertainties, the fossil record establishes several important facts. Ekgmowechashala successfully survived in North America for at least some millions of years after its arrival. Fossils recovered from both Nebraska and Oregon indicate that its range extended well beyond a single isolated locality, suggesting a population capable of spreading across portions of the Western continent despite unfamiliar environmental conditions. Eventually, that record ends as completely as it began. Ekgmowechashala disappeared without leaving known descendants in North America. After its final appearance, the continent once again remained without non-human primates for approximately 27 million years, until members of our own species eventually entered through the same northern passage that had carried this remarkable traveler so many millions of years before. Every lineage eventually reaches a point where its fossils end. For Ekgmowechashala, that closing chapter stretched across only a brief interval of geological time. The earliest known specimens appear near the beginning of the Araucarian North American land mammal age, approximately 29.5 million years ago. Fossils discovered farther west in Oregon show that the species endured for some millions of years afterward, with the youngest known remains approaching roughly 27 to 28 million years in age. Then the record comes to an abrupt conclusion. Its disappearance marked the second and final loss of non-human primates from North America. The earlier extinction at the close of the Eocene had eventually been followed by an unexpected return from Asia. This time, no comparable refuge produced another successor. No later immigrant lineage crossed the northern land connection to restore primates to the continent. After Ekgmowechashala vanished, North America entered a span unlike anything it had experienced before. The continent itself continued changing. Conditions that had begun shifting during the previous climatic transition advanced even farther. Forests occupied a smaller share of the landscape, while open environments spread across broad regions. Cooler temperatures, increasing dryness, and stronger seasonal cycles favored mammals adapted to traveling long distances across expanding plains. These ecological pressures steadily reshaped animal communities into forms better suited for life beyond continuous forest canopies. Large grazing mammals flourished within that changing world. Horses diversified into numerous forms, camels expanded across western landscapes, and many millions of years later, enormous herds of bison and mammoths would roam those same plains. The continent increasingly rewarded speed, endurance, and the efficient use of open habitats. Such environments offered far fewer opportunities for small arboreal primates whose ancestors had evolved among branches rich with fruit and shelter. Exactly why Ekgmowechashala disappeared remains uncertain. The available fossils preserve no final moment and reveal no single catastrophic event. Gradual habitat loss, changing food resources, climatic pressures, or competition with other mammals may all have contributed. The evidence supports only the outcome. At some point near the close of its known record, the lineage vanished completely from North America, leaving no descendants and no subsequent fossil evidence of its continued survival. From approximately 27 million years ago onward, the continent became entirely devoid of primates. That absence continued until members of our own species eventually crossed Beringia between roughly 14,000 and 20,000 years ago. Across that immense interval, countless mammals evolved, flourished, and disappeared, while no primate left so much as a single confirmed fossil within North America. The scale of that gap is difficult to appreciate through ordinary experience. Approximately 27 million years separate the disappearance of Ekgmowechashala from the arrival of human beings. That interval exceeds the entire evolutionary history of the genus Homo by more than a factor of 10. Species rose and vanished. Mountain ranges continued changing. Climates shifted repeatedly, and ecosystems transformed many times, while primates remained completely absent from the continent. North America had once supported a primate history extending across roughly 20 million years, beginning with the earliest arrivals during the Eocene and ending with one remarkable immigrant from Asia. After that final disappearance, the continent spent an even longer stretch without any primate presence at all. Measured against such deep time, the human chapter occupies only the closing lines of an immense geological narrative, written after millions upon millions of years, during which no grasping primate hand left a trace upon the land. The history of primates unfolded along two neighboring continents, yet their paths gradually separated until they scarcely resembled one another. After North America lost its native primates and later its remarkable Asian immigrant, South America followed an entirely different course. Comparing those parallel histories reveals how profoundly geography and climate shaped the destiny of entire branches of the primate family. The primates of South America did not descend from the adapiforms that once occupied North America. They belonged to an independent radiation known as the platyrrhines, commonly called the New World monkeys. Their ancestors almost certainly reached South America from Africa between approximately 35 and 40 million years ago. At that time, the Atlantic Ocean separating the continents remained considerably narrower than it is today. Floating masses of uprooted vegetation, carried westward by currents after powerful storms or floods, likely transported small mammals across the water during one of evolution's most extraordinary journeys. Once established, those early arrivals encountered a continent offering opportunities unavailable farther north. Throughout much of the Oligocene and Miocene, South America retained extensive forests across large tropical regions. Its lower latitude moderated the effects of the global cooling that transformed ecosystems elsewhere. Although climatic change certainly influenced the continent, it escaped the sweeping forest collapse that reshaped North America after the beginning of large Antarctic ice sheets. Those comparatively favorable conditions allowed South American primates to diversify across millions of years. New branches appeared again and again, filling different ecological roles within forests that continued providing fruit, leaves, flowers, insects, and sheltered canopies. The descendants of those pioneering immigrants eventually produced howler monkeys, spider monkeys, capuchins, marmosets, tamarins, and euacaris, each representing an evolutionary experiment carried out in long geographic isolation. Their story demonstrates what sustained forests could accomplish when primate lineages remained connected to suitable habitat across immense spans of time. North America experienced the opposite trajectory. Cooling climates steadily reduced continuous forest cover, while open woodlands and expanding grasslands spread across much of the continent. The ecological foundation supporting earlier primate communities gradually disappeared. Even the later arrival of Ekgmowechashala could not permanently reverse that transformation. The continent increasingly favored mammals, adapted to open environments instead of species whose evolutionary heritage remained closely tied to life among trees. For most of this history, the two American continents remained separated by open water. A complete land bridge did not exist until approximately 3 million years ago, when the Isthmus of Panama fully connected North and South America. That geological event triggered one of Earth's great episodes of faunal exchange as mammals moved between the continents in both directions. Certain New World monkeys expanded into portions of Central America, extending their distribution farther north than ever before. Even then, none established enduring populations within North America itself. By the time the land bridge formed, the continent had already existed without primates for approximately 24 million years. The environmental conditions that had eliminated earlier lineages still differed greatly from those supporting monkey populations farther south. Seen together, the two continents preserve complementary chapters of a single evolutionary story. South America illustrates how primates flourished when forests remained extensive and climatic disruption proved less severe. North America records the opposite outcome, where global cooling permanently altered ecosystems and ended an ancient lineage. Their contrasting histories trace back to climatic changes that began when Antarctica became locked beneath expanding ice, reshaping environments across the world and determining which primate dynasties would continue and which would become only fossils preserved within stone. Every fossil carries two histories. One belongs to the animal that lived millions of years ago. The other belongs to the people who eventually recognized its significance after lifting it from layers of stone. North America's ancient primates have emerged through the work of generations of paleontologists whose discoveries, separated by decades and continents, gradually assembled a story that no single expedition could ever have revealed. The modern record began with Joseph Leidy, a physician and naturalist in Philadelphia whose interests extended far beyond medicine. In 1870, working with fragmentary fossil material collected from western North America, he formally described Notharctus. Vertebrate paleontology remained a young scientific discipline, and many prehistoric mammals were still unfamiliar to science. The fossils available to Leidy were incomplete, yet they established the existence of an ancient North American primate and opened a field of research that would continue for generations. Field exploration expanded dramatically during the early years of the 20th century. Walter Granger, working for the American Museum of Natural History, spent many seasons searching the Bridger Basin of Wyoming. Patient excavation across broad exposures of Eocene rock yielded dozens of Notharctus specimens, including skeletons far more complete than those previously known. For the first time, researchers could examine much of the animal's body instead of relying mainly upon isolated teeth and scattered bones. Those discoveries transformed an obscure fossil into a recognizable primate with identifiable anatomy and habits. The growing collection soon became the foundation for another milestone. In 1920, William King Gregory produced a landmark anatomical study based largely upon Granger's remarkable material. Through careful comparisons with living and fossil primates, Gregory demonstrated where North America's Eocene primates belonged within the broader primate family tree. His work established a comparative framework that guided researchers for approximately a century, allowing future discoveries to be evaluated against carefully documented anatomical standards. That foundation eventually made it possible to solve the mystery of Ekgmowechashala. Kathleen Rust at the University of Kansas, together with collaborators from the Institute of Vertebrate Paleontology and Paleoanthropology in Beijing, combined fossil evidence collected from two countries separated by nearly 10,000 miles. The connection depended upon remarkably subtle anatomical features, especially dental characteristics measured in fractions of a millimeter. Those minute details revealed relationships that had remained hidden through 6 decades of investigation, demonstrating how discoveries made on different continents could finally complete the same evolutionary puzzle. The landscapes preserving these fossils deserve recognition alongside the scientists themselves. The Bridger Basin and Bighorn Basin of Wyoming continue exposing sediments laid down during the Eocene. Farther east, Nebraska's White River Formation preserves the younger Oligocene environments that yielded Ekgmowechashala. Across Oregon, the John Day Formation contributes additional evidence from that same interval. Together, these fossil-bearing formations extend across thousands of square miles, recording ecosystems that changed over millions of years while preserving countless fragments of the animals that inhabited them. Researchers have returned to these places season after season since the 1870s. Each expedition uncovers new specimens, refines earlier interpretations, or occasionally reveals species previously unknown to science. Even collections gathered decades ago continue yielding discoveries when re-examined with modern techniques and fresh questions. For that reason, the fossil record remains an unfinished archive rather than a completed book. Every newly exposed hillside, every carefully prepared tooth, and every overlooked specimen resting within a museum drawer carries the possibility of extending the story. The rocks have never stopped preserving evidence. Human understanding continues advancing only as quickly as patient hands are able to uncover what has been waiting there all along. Many of the fossils that transformed our understanding of North America's ancient primates have rested inside museum collections for decades, some for more than a century. Their importance has not changed, yet the tools used to examine them have advanced dramatically. Today, paleontologists often discover entirely new information without removing another fragment of rock, allowing specimens collected long ago to continue revealing details that earlier generations could never have observed. One of the greatest advances has come through high-resolution computed tomography scanning. These systems allow researchers to peer inside fossils without damaging them, creating detailed three-dimensional digital reconstructions while leaving every grain of surrounding rock undisturbed. Rare specimens remain physically intact, preserving irreplaceable material for future study while simultaneously yielding anatomical information that once required destructive preparation techniques. That approach demonstrated its remarkable potential in 2016 when researchers from Duke University and the University of Toronto reconstructed the brains of Notharctus, Tenebrosus, and Smilodectes gracilis. Although the original brain tissue had vanished approximately 47 million years earlier, subtle impressions preserved inside the skulls remained. High-resolution computed tomography transformed those impressions into virtual endocasts, producing three-dimensional models that revealed the overall shape and organization of brains belonging to animals that disappeared long before human beings existed. Features, once hidden within solid stone, became accessible with extraordinary clarity. Other techniques examine chemistry instead of anatomy. Carbon and oxygen isotope analysis performed on fossil tooth enamel can reconstruct aspects of an individual's diet throughout its lifetime. Those chemical signatures reveal more than preferred foods. Seasonal variations recorded within the enamel may indicate changing feeding habits as environmental conditions shifted during the year. Such evidence offers glimpses of behavior that bones alone cannot preserve. Strontium isotope analysis provides another perspective. The ratio of naturally occurring strontium isotopes incorporated into growing teeth reflects the local geology of the water an animal consumed while those teeth formed. Because different landscapes possess distinctive geological signatures, fossil teeth sometimes preserve evidence of movement across regions during an individual's lifetime. A single tooth may therefore contain a geographical record extending far beyond the place where the fossil was ultimately buried. Microcomputed tomography has expanded the range of anatomical questions that researchers can investigate. Extremely fine scans of jaws and surrounding structures allow scientists to infer the arrangement of muscles associated with the tongue, cheeks, and other soft tissues that disappeared millions of years ago. Although those tissues themselves are absent, the bone preserves attachment sites and subtle structural relationships that permit increasingly sophisticated reconstructions of feeding behavior and oral function. Perhaps the newest frontier reaches beyond anatomy altogether. Tiny fragments of ancient proteins, preserved within fossil tooth enamel, have begun providing evolutionary information unavailable through deoxyribonucleic acid. Under most natural conditions, deoxyribonucleic acid breaks down after only a few million years, placing many ancient fossils beyond its reach. Certain enamel proteins, however, survive much longer, extending the possibility of reconstructing evolutionary relationships far deeper into Earth's history than previously imagined. Applied together, these methods steadily sharpen the picture emerging from fossils collected in Wyoming, Nebraska, and Oregon. Specimens that once revealed little more than external shape now preserve anatomical, chemical, developmental, and evolutionary information with astonishing precision. Each technological advance answers questions that once seemed permanently beyond reach, while opening entirely new avenues of investigation. The fossils themselves have remained unchanged throughout that time. What continues evolving is humanity's ability to read the stories they have carried since the Oligocene and the Eocene first became stone. Evolution leaves behind more than fossils. It also leaves patterns, directions, and possibilities that can be traced through anatomy, even when their final destination remains forever beyond observation. The ancient primates of North America had already begun following a recognizable evolutionary course before climate closed that chapter. Their preserved skeletons and the digital reconstructions of their skulls reveal a lineage that was changing in ways familiar from other branches of the primate family. The evidence preserved within their skulls points toward an established neurological trend. Studies of virtual endocasts show increasing emphasis on regions of the brain devoted to vision, while areas associated primarily with smell occupied a relatively smaller role than in many earlier mammals. Such reorganization reflects a growing dependence on visually guided movement through complex environments. It belongs to the same broad pattern observed among primates living in Africa and Asia, where comparable neurological changes eventually formed part of the long evolutionary path leading toward greater cognitive complexity. That direction, however, should never be mistaken for certainty. Evolution has no predetermined destination. Countless lineages develop similar anatomical features while arriving at very different outcomes. Even so, the North American primates had already entered a well-documented trajectory shared across much of the primate family, one that in distant relatives ultimately accompanied increasingly elaborate social behavior, more sophisticated communication, and, in one branch, many millions of years later, the emergence of human language and thought. Their continent also occupied a distinctive geographical setting. Throughout much of the Eocene, North America evolved in relative biological isolation. South America remained separated by broad seaways, while contact with Asia occurred only intermittently through Beringia. That pattern resembles the evolutionary circumstances of islands, where long periods of separation often encourage unique biological experiments, unlike those developing elsewhere. Evolutionary history provides many examples of such isolation. Australia's marsupials diversified along paths unlike those followed by placental mammals on other continents. Madagascar's lemurs developed remarkable forms after becoming separated from their African relatives. The finches of the Galapagos Islands became one of the clearest demonstrations of how isolated populations gradually diverge through adaptation to different ecological opportunities. Geographic separation repeatedly generates unexpected evolutionary outcomes. Had North America's primates continued evolving within their comparatively isolated continent for another 20 or 30 million years, their descendants might have followed directions impossible to predict today. They would have encountered ecological challenges, unlike those shaping monkeys and apes developing simultaneously in Africa. Without direct competition from those later lineages, entirely different combinations of anatomy, behavior, and social organization might have emerged. No fossil, no mathematical model, and no biological principle can reconstruct an evolutionary future that never occurred. The fossil record therefore reaches a natural boundary. It reveals the direction with remarkable confidence while remaining unable to describe the destination. That distinction is essential. Scientific evidence supports careful reconstruction of evolutionary trends, yet it cannot transform unrealized possibilities into historical fact. One conclusion, however, stands upon firm ground. The North American lineage did not disappear because its evolutionary potential had been exhausted. Nothing preserved within its anatomy suggests an unavoidable dead end. Its history was interrupted by environmental transformation, driven largely by changing ocean circulation and the expansion of Antarctic ice, processes unfolding far beyond the experience of any primate. Those global changes steadily reshaped climates and forests across continents until the ecological foundation supporting that lineage no longer remained. The road left behind was never demonstrated to be lesser or greater than the one preserved elsewhere. It became unknowable because the planet itself closed that path before evolution had the opportunity to discover where it might eventually have led. Some chapters of Earth's history are remembered because they explain the past. Others remain important because they also illuminate the present. The Eocene belongs to both. Its rocks preserve one of the clearest records of how a planet responds when atmospheric carbon dioxide remains far above the levels familiar today, making those ancient landscapes valuable not only to paleontologists, but also to scientists studying Earth's changing climate. During the warmest intervals of the Eocene, atmospheric carbon dioxide reached approximately 885 parts per million. Modern measurements recorded during the middle of the 2020s have risen to roughly 420 to 425 parts per million, already more than one half higher than the approximately 280 parts per million estimated before widespread industrial emissions began. Those values continue increasing, placing renewed scientific attention upon ancient climates that experienced substantially different atmospheric conditions. The Eocene demonstrates with remarkable clarity the kinds of ecosystems that developed beneath sustained concentrations of atmospheric carbon dioxide. Palm trees flourished in what is now Montana. Subtropical forests covered regions of Wyoming that today experience cold winters. Crocodilian relatives inhabited areas extending into the Arctic. Across much of the planet, warm conditions supported abundant forests and rich biological communities. Species adapted to those environments prospered because the world around them matched the conditions under which they had evolved. The fossil record also preserves the opposite transition. As atmospheric carbon dioxide declined near the boundary between the Eocene and Oligocene, Antarctica accumulated expanding ice sheets, global temperatures fell, and ecosystems reorganized across continents. Europe experienced the biological turnover known as the Grande Coupure, while North America witnessed widespread ecological transformation. Approximately one half of mammalian genera disappeared during this interval, and the continent's long established primate lineage ultimately vanished after nearly 20 million years of successful occupation. Taken together, these events offer a broader lesson than either warming or cooling considered alone. The fossil evidence shows that large-scale climatic change, moving in either direction and unfolding more rapidly than evolutionary adaptation can keep pace with, reshapes habitats, food webs, and entire biological communities. Species become finely tuned to particular environmental conditions across many generations. When those conditions shift beyond the range that previous adaptations can accommodate, even lineages that have thrived for millions of years may struggle to persist. North America's ancient primates illustrate that principle with unusual clarity. Their anatomy, behavior, and ecology had become well suited to the forested landscapes of the Eocene. For approximately 20 million years, those adaptations supported successful populations across broad regions of the continent. Their disappearance did not reflect weakness or biological inadequacy. Instead, the environmental framework supporting that success changed more rapidly than accumulated evolutionary adjustments could compensate. A lineage shaped by one world found itself living within another. That perspective lends unusual significance to these fossils. They preserve more than extinct animals or vanished forests. They document how living systems respond when the physical environment undergoes profound transformation. The details differ across every geological age, yet the underlying relationship between climate and life remains inseparable. The rocks cannot predict the future, nor can they identify which modern species will ultimately adapt, migrate, decline, or flourish as environmental conditions continue changing. They provide something equally valuable. They preserve an unmistakable record that life and climate have always evolved together, and that when the planet enters a new chapter, every organism already living upon it must meet a world that is no longer exactly the one to which it was once so perfectly fitted. A landscape can appear to tell one story while preserving another far older beneath its surface. Across parts of Wyoming and Oregon, broad expanses of weathered hills, exposed cliffs, and dry valleys seem perfectly suited to the climates of today. Yet every layer of stone beneath those open skies protects the remains of ecosystems so different that they almost defy imagination. These rocks are not merely ancient. They are the last surviving archive of North America's vanished primate world. In southwestern Wyoming, the Bridger Basin stretches across pale gray and buff sediments shaped by wind, frost, and seasonal rain. Sagebrush grows across slopes that receive little moisture, while exposed ridges reveal sediment deposited approximately 50 million years ago. During the Eocene, however, those same sediments formed the floor of a warm subtropical forest. Towering trees, shaded streams, and wetlands, broad leaves collected sunlight overhead, and primates traveled through connected canopies that no longer exist. Every fossil recovered from these rocks comes from ground that once supported an entirely different living landscape. Farther north, the Bighorn Basin preserves one of the most thoroughly studied sequences of Paleocene and Eocene rocks anywhere in the world. Here, The geological layers recording the Paleocene-Eocene thermal maximum remain exposed at the surface, allowing researchers to examine the interval during which primates first appeared in North America. Each field season adds new observations as paleontologists carefully excavate sediments deposited during those transformative thousands of years. The sequence records changing climates, shifting ecosystems, and the earliest steps of a lineage that would eventually spread across much of the continent. The story reaches its closing pages within Oregon's John Day Formation. Those rocks preserve the Oligocene landscapes where Ekgmowechashala struggled to survive after returning from Asia. Fossils recovered there document the youngest known representatives of North America's final native primate lineage. The surrounding terrain now bears little resemblance to the habitats those animals inhabited. Millions of years of uplift, erosion, climatic change, and ecological turnover have replaced ancient forests with landscapes shaped by entirely different environmental forces. Standing within any of these fossil localities creates an unusual contrast between observation and knowledge. The hills reveal almost nothing of the forests they once supported. Modern vegetation offers no visual reminder of broad canopies stretching overhead. The animals crossing these valleys today belong to ecosystems assembled long after the primates disappeared. Even the atmosphere carries different seasonal rhythms than the climates recorded within the rocks below. Without the fossils themselves, almost no evidence visible on the surface would suggest that these places once belonged to another biological world. That is why fossils possess such extraordinary importance. They are the only surviving physical memory the land has retained. Bone buried beneath accumulating sediment endured compression, mineral replacement, uplift, erosion, and the passage of approximately 50 million years before returning once more to daylight. Entire forests vanished without leaving recognizable traces, yet a single tooth or fragment of jaw survived those immense spans of geological time. When a paleontologist carefully uncovers a primate tooth from Wyoming clay, that small fossil becomes far more than a specimen. It is the lone surviving witness to a continent transformed beyond recognition, the only physical object capable of proving that North America once supported forests filled with primates whose world disappeared so completely that only the rocks still remember where they lived. Across Earth's history, extinction is often imagined as a judgment upon the creatures that disappear. The fossil record offers a different perspective. Again and again, it shows flourishing lineages occupying successful environments for immense stretches of time, only to fade when the world surrounding them changes beyond the limits of their accumulated adaptations. North America's ancient primates belong among the clearest examples of that enduring pattern. Their disappearance did not arise from biological inadequacy. For approximately 20 million years, they expanded across forests that stretched over much of the continent. They occupied diverse habitats, developed specialized diets, refined agile movement through complex canopies, and displayed the neurological trends characteristic of early primate evolution. Their communities included numerous species living alongside equally successful mammals, birds, reptiles, and flowering plants. Every available measure preserved within the fossil record indicates a lineage thriving within the environmental conditions that shaped it. Success in evolution, however, carries a meaning unlike success in ordinary human experience. It offers no lasting guarantee and provides no permanent security. Instead, it describes a relationship between living organisms and the environments supporting them at a particular moment in geological time. As long as that relationship remains favorable, populations grow, diversify, and persist across countless generations. When the surrounding world changes beyond the pace that adaptation can accommodate, even remarkably successful lineages may disappear. The transformation that overtook North America's primates unfolded across hundreds of thousands of years, astonishingly rapid from the perspective of geological history. Although vastly longer than any human civilization has existed, expanding Antarctic ice altered global ocean circulation, atmospheric patterns, rainfall, and vegetation across continents. Those changes originated far from the forests inhabited by the primates themselves, yet the consequences gradually reached every ecosystem connected through Earth's climate. No behavioral flexibility or inherited adaptation could fully compensate for environmental shifts occurring across an entire planet. The brief arrival of Ekgmowechashala after millions of years of absence gives this history an especially poignant final chapter. Descended from Asian relatives, it crossed into North America through a temporary land connection and established small populations within habitats already transformed by long continuing climatic change. Its presence demonstrated that dispersal remained possible even after the original native primates had vanished. Yet, the ecological foundation supporting earlier primate diversity had already disappeared. The newcomers survived only a comparatively short interval before joining the long list of species preserved solely within stone. After that final disappearance, the continent entered an interval unlike any previous chapter in its natural history. Forests yielded increasing space to open landscapes. Grazing mammals multiplied across expanding grasslands, followed by predators adapted to those changing environments. New ecological communities flourished, rich with their own interactions, migrations, and evolutionary innovations. The continent did not become empty. It simply belonged to different forms of life than those that had occupied it before. Throughout approximately 27 million years that followed, no primate established an enduring presence anywhere across North America. No grasping hands reached through forest branches. No forward-facing eyes surveyed canopies from above. No native lineage continued the gradual neurological changes once visible within the Eocene fossil record. The continent carried forward an entirely different biological story until human beings eventually arrived from Asia during the closing chapters of the Ice Age. The rocks preserve that immense interval with remarkable honesty. They show neither triumph nor failure. They record only the changing relationship between life and the planet that sustains it, reminding us that every successful lineage, regardless of how long it prospers, ultimately depends upon a world that never remains exactly the same forever. The distance separating living people from North America's earliest primates is measured in tens of millions of years, yet the connection between them is written into the branching pattern of the primate family itself. Those Eocene animals did not belong to the direct ancestral line that eventually produced humanity. Their story followed neighboring branches, diverging long before our own lineage began its separate journey. Even so, they remained members of the same remarkable evolutionary radiation whose descendants still inhabit forests, islands, mountains, and cities across the modern world. The adapiforms, including Notharctus, Smilodectes, and Cantius, occupied the branch leading toward today's lemurs and lorises. They were not early monkeys or primitive humans. Their descendants did not continue toward the African lineages that ultimately produced apes. Yet the body plans they carried already displayed the defining features of primates. Grasping hands wrapped around branches with precision. Forward-facing eyes gathered overlapping fields of vision. Brains gradually expanded regions devoted to processing complex visual information. Their daily lives depended increasingly upon flexible behavior and enduring social relationships instead of fixed instinctive responses alone. Sharing those forests were the omomyiforms, a different group whose evolutionary position lay closer to the branch, eventually leading toward humanity. Their large eyes reflected lives spent navigating dimly lit canopies, searching for insects and other small prey. Modern evidence places them within the haplorhine side of the primate family tree, the lineage that includes living tarsiers, monkeys, apes, and eventually the genus that would stand upright upon African grasslands while developing language, culture, and the ability to investigate its own origins. The geography linking these histories stretches across astonishing spans of time. Beringia served as a bridge more than once, though the travelers crossing it belonged to very different ages. Early primates, such as Teilhardina, reached North America through that northern connection during the Eocene. Much later, Ekgmowechashala entered the continent after millions of years without native primates. Far afterward, during the Ice Age, the ancestors of every indigenous people of the Americas also crossed through Beringia, carrying traditions, knowledge, and communities that would flourish across an entire hemisphere. Their arrival left comparatively little fossil evidence, yet its historical significance equals any preserved within the rocks. From a biological perspective, those first human populations became the earliest primates to establish a lasting presence in North America since Ekgmowechashala disappeared approximately 27 million years earlier. Between those distant moments stretched one of the longest intervals during which an entire continent lacked members of the primate order. Human beings succeeded where earlier primates could not because they possessed abilities unlike any previous lineage. Fire provided warmth beyond natural climates. Clothing extended survival into colder regions. Shared knowledge allowed food sources, migration routes, and seasonal changes to be remembered across generations instead of rediscovered anew. None of those travelers could have known they were entering a continent that once supported thriving primate communities. The valleys, plains, mountains, and forests revealed nothing of the much older inhabitants preserved far below their feet. No visible landmark hinted that grasping hands had once moved through Eocene canopies across the same broad landmass. The evidence remained sealed within stone, awaiting discovery by descendants of a primate lineage whose defining characteristic had become persistent curiosity about the natural world. When paleontologists finally uncovered those fossils, the continent revealed a forgotten chapter connecting distant cousins across immense stretches of time. The bones did not transform humans into descendants of North America's earliest primates. They revealed something equally profound, that long before our own footsteps reached this landscape, other members of our wider primate family had already called it home. There comes a point in every journey through Earth's history when numbers stop behaving like measurements and begin behaving like landscapes of their own. They stretch so far beyond ordinary experience that the mind can no longer compare them with familiar history. Instead, they ask for patience, inviting each passing million years to settle gradually into perspective until the scale itself becomes part of the story. Approximately 56 million years ago belongs to that kind of time span. It is separated from the present by far more than the rise and fall of civilizations or the appearance of written language. During that distant age, continents occupied different positions than they do today. Ocean currents followed different pathways across the globe. Atmospheric chemistry sustained climates, unlike those surrounding us now. The region known today as Wyoming lay beneath skies that illuminated forests bearing almost no resemblance to the landscapes familiar across the modern American West. Within those forests lived real animals, each carrying out an ordinary existence, entirely unaware of the immense history that would follow. They searched for fruit, leaves, insects, and flowers. They escaped predators, cared for offspring, formed social bonds, and traveled through branches that seemed as permanent to them as any environment appears to its inhabitants. Their lives unfolded one sunrise after another within ecosystems that, from their perspective, defined the whole of existence. Generation followed generation across approximately 20 million years. Forest communities changed gradually while preserving the ecological relationships supporting those primates. Their evolutionary history accumulated across spans so immense that entire mountain ranges experienced erosion while the lineage itself continued. Then, within what geology recognizes as a comparatively brief interval, climatic transformation altered the conditions sustaining that success. Native primates disappeared from the continent. Millions of years later, one immigrant lineage briefly restored the presence of the order before disappearing once more, leaving North America without primates for approximately 27 million years. When viewed beside that absence, the human story occupies an unexpectedly small space. Every migration across Beringia, every settlement, every civilization, every language, every discovery, every conflict, and every generation born upon this continent fits comfortably within that much longer interval during which no primate lived here at all. The comparison does not diminish humanity. Instead, it reveals the astonishing scale across which Earth's history unfolds. Deep time reshapes perspective in subtle ways. It reminds us that permanence is often an impression created by limited experience rather than an enduring feature of nature itself. Landscapes that appear fixed continue changing. Climates regarded as familiar represent only one chapter among countless others. Ecosystems flourishing today exist within conditions that, over geological spans, will continue evolving as they always have. The Eocene forests almost certainly felt complete to every creature living within them. Nothing in the daily routines of those primates suggested that their world belonged to a temporary chapter. Food remained available. Seasons returned in familiar rhythms. Young animals matured, adults reproduced, and forests renewed themselves across generations beyond counting. Every observable pattern reinforced the impression of continuity, because those patterns had endured for longer than any individual life could imagine. Even so, the Earth continued following processes extending far beyond the awareness of any organism inhabiting its surface. Oceans shifted, continents drifted, climates transformed, and biological communities adjusted as new conditions emerged. The forests eventually disappeared, yet the memory of their existence remained preserved within stone until another primate lineage, one capable of reading rocks and measuring time itself, uncovered the evidence and recognized that every present world, no matter how enduring it seems, ultimately belongs to a much longer story still being written. Late afternoon transforms the Bridger Basin into a landscape of long shadows and pale stone. Layer after layer of weathered sediment stretches across the horizon in broad horizontal bands, each one marking the passage of another chapter in Earth's history. The hills appear almost sculpted by time itself, carved into ridges and gullies that reveal millions of years with remarkable clarity. From a distance, the terrain seems detached from every familiar image of living forests, inviting the impression that it belongs to another world entirely. Nothing within that view suggests dense vegetation once flourished here. No towering canopy arches overhead. No broad leaves gather sunlight across interconnected branches. Tens of millions of years have passed since forests of that kind covered this region. Sagebrush now rises as the tallest common vegetation across broad expanses of open ground. Dry air carries little resemblance to the humid conditions that once sustained abundant plant life. Standing within the basin today, the thought of a subtropical forest feels separated from the present by more than time alone. It seems almost impossible that both landscapes could occupy the same ground. Yet, the evidence remains exactly where that vanished ecosystem left it. Beneath every exposed slope lie sediments that accumulated gradually along ancient rivers, floodplains, lakes, and wetlands. Leaves settled upon damp soil, fine mud-covered fallen branches. Floodwaters spread fresh layers across the forest floor. Bones, teeth, and fragments of skeleton became buried within those deposits, protected from scavengers and weather until the slow processes of mineralization transformed them into fossils. Compression, uplift, and erosion altered everything surrounding them, while the fossils themselves endured through approximately 50 million years of geological change. Each primate tooth recovered from Wyoming carries an importance far beyond its modest size. That tiny piece of enamel becomes direct physical evidence that this continent once supported ecosystems unlike anything visible across the modern landscape. It confirms that grasping hands once reached among branches growing above the very ground now crossed by pronghorn, mule deer, and coyotes. It demonstrates that forward-facing eyes once watched a forest canopy occupying terrain where open skies now extend uninterrupted across distant ridges. The modern surface offers remarkably few clues about that earlier world. Its plants belong to different climates. Its animals participate in different ecological relationships. Its streams follow channels shaped long after the Eocene forests disappeared. If every fossil vanished tomorrow, almost nothing visible within the landscape would reveal that primates had ever lived there at all. The transformation has been so complete that the present environment preserves almost no biological resemblance to the one recorded beneath it. That contrast reveals an important distinction between landscape and geology. Landscapes respond continuously to changing climates, shifting vegetation, erosion, and the movement of living communities. Geology preserves evidence with far greater patience. Stone retains events long after the surface has exchanged one ecosystem for another many times over. The work of paleontology depends upon reading those preserved layers instead of relying upon appearances visible today. Every excavation becomes an act of listening to records written beneath the modern world rather than upon it. The ground beneath a visitor's feet belongs to the present, shaped by climates and living communities existing now. The rock extending downward preserves every earlier chapter layered beneath that familiar surface. Within those buried pages rests the memory of a North American primate world that flourished for approximately 20 million years, disappeared without leaving descendants upon the continent, and survived only because stone remembered what the living landscape eventually forgot. Approximately 56 million years ago, an animal weighing little more than a single ounce crossed a forested land bridge connecting Asia and North America. It carried no awareness that its journey marked the beginning of one of the longest chapters in the continent's biological history. Beyond that crossing waited forests shaped by warmth, abundant rainfall, and towering trees. The world it entered matched the abilities its ancestors had refined through countless generations, offering branches to climb, fruit to gather, insects to pursue, and an expanding landscape where primates had never lived before. From that modest beginning grew a remarkable evolutionary story. Across approximately 20 million years, North America's primates diversified into many forms, each adapting to different ecological opportunities within broad forest ecosystems. Some specialized in leaves, others in fruit or insects. Their brains gradually reorganized toward increasingly sophisticated visual processing. Social relationships became more flexible and enduring. Across the wider primate family, spreading through several continents, evolutionary foundations continued developing that would eventually support monkeys, apes, and, much later, human beings. Far from those forests, another transformation had already begun. Antarctica accumulated expanding ice sheets that altered ocean circulation, atmospheric patterns, and global climate. Forests slowly withdrew as cooler and drier conditions spread across North America. Suitable habitat became increasingly fragmented. Populations contracted from one forest to another, then into still smaller refuges until the fossil record finally reached its last native representatives. After flourishing across immense spans of geological time, the continent's original primate communities disappeared. Millions of years later, another member of the primate order returned. Descended from relatives that had persisted within southern Asia, Ekgmowechashala crossed into North America through a northern connection resembling the route used by much earlier primates. Its arrival briefly restored a presence that had already vanished from the continent. The environment awaiting it, however, differed profoundly from the warm forests that once supported abundant primate diversity. Its lineage endured only a comparatively short interval before disappearing as well, closing the final chapter of North America's prehistoric primates. Approximately 27 million years followed without a single native primate inhabiting the continent. During that immense interval, mountains continued rising and eroding, rivers shifted course, grasslands expanded and contracted. Countless generations of mammals, birds, reptiles, and flowering plants appeared, diversified, and disappeared. The absence of primates lasted far longer than the entire span of recorded human history. Eventually, another crossing through Beringia took place. Human ancestors entered North America carrying abilities unlike those possessed by any previous primate. Fire extended warmth beyond favorable climates. Clothing reduced dependence upon natural conditions. Shared knowledge allowed experience gathered by one generation to strengthen the survival of the next. Through culture as much as biology, humanity succeeded in environments that earlier primates could never have occupied for long. Those first travelers could not have known they were stepping onto land with a primate history reaching tens of millions of years beyond their own lineage. Nothing visible upon the surface revealed that forgotten inheritance. The evidence remained preserved within Wyoming sediments, Nebraska clay, and Oregon rock formations, where generations of paleontologists would eventually uncover it with careful hands and patient observation. Stone preserved what living landscapes could no longer display. Fossils endured until another primate lineage developed both the curiosity to search for them and the knowledge to understand what they meant. In that moment, separated by approximately 56 million years from the first tiny traveler entering North America, the longest story came full circle, connecting the continent's earliest primates with the descendants who finally learned how to read their memory from the rocks.